Okay, so now we're going to get into the the motivation for studying thermodynamics in the first place. Okay, the the steam power plant is responsible for a vast majority of the electricity generated across the globe today. All right, so literally, quite seriously, this what we're about to get into is responsible for modern life. Okay, this is where our electricity comes from, for the most part. Whether we're burning coal or using nuclear power, that's just the source of heat. The underlying mechanism by which we actually produce the work is a heat engine. Is what's called a heat engine. Now, a heat engine is really nothing more than the combination of a certain number of devices, steady flow devices typically, arranged in such a way that they can operate in a cycle, a thermodynamic cycle, and produce a net amount of work um, by absorbing or taking in a certain amount of heat. So it converts heat into work. And as we'll get into a little bit later, it not only creates work, it also has to reject some heat. So it basically takes a temperature difference, if you will, takes a temperature difference, um, draws in heat on the hot side, produces certain amount of work, and pushes out heat on the cold side. Um, that's what a steam power plant does. And so some of that work, it gets recycled back into a pump that pumps the fluid and keeps the cycle going. But for the simple explanation is that we're going to take heat and we're going to produce work. That's what heat engines do, and that's essentially what powers modern life. Okay, so um, the elements associated with the steam power plant. So this is a simple representation of a steam power plant and the minimum number of components that are required to run it. Modern power plants are usually a lot more complicated. You have multi-stage turbines and maybe intercoolers or heat regeneration devices and stuff like that. But we're going to focus on the simple one. All right. And so there's some quantities associated with steam power plants that we're going to need to be familiar with. Notice the change of notation. Rather than talking about Q in and Q out, I'm going to talk about the heat at the hot side and the heat at the cold side, which I annotate with H for high temperature and L for low temperature. Okay, so the low temperature is given by TL, the high temperature is TH, and the heat absorbed at the hot side is QH and QL. Now, the reason for this is will become clear later, but just understand that in the case of a power plant, heat is being rejected to the cold side and being brought in at the hot side, which makes sense, right? You burn something hot, you extract heat from that, pull out a little bit of work, and then you have to reject some heat to the cold side. All right, so we're going to define a couple quantities. So there's the net work is equal to the output work minus the input work. Okay, that's the definition of net. So just like your net pay. However, notice I have a system here, right? And I have the boundary. If I use this outer boundary, the first law still applies. Okay, so the input work plus the input heat has got to be equal to, in the case of a steady operation, the output work plus the rejected heat. Okay, so I can rewrite this I can rewrite the net work in terms of a difference in the heats, the hot side versus the cold side. All right. And so I'm going to define efficiency in general. All right. Efficiency is usually given the symbol, the Greek letter eta, and it's always a desired quantity divided by the cost. And by convention, it's less than 1, typically less than 1. So if you see efficiency is greater than 1, that's usually a sign that your calculation's off. So we're going to define thermal efficiency, which is a eta with a little subscript th. And we're going to define it just like we did here. So the desired quantity in this case is going to be the net work out. And the cost is the heat input in. Okay? Again, efficiency is a dimensionless quantity. So the desired quantity and the cost have to have the same units. In this case, we got power divided by power is unitless. All right. So I can rewrite this using this expression here. Cancel out the q dot h's, and I just get 1 minus the ratio of the heat rejected on the cold side over the heat absorbed on the hot side. Okay, so that's thermal efficiency. And so that's all I really want to say about that, I suppose. So we've defined these quantities, and I've talked a little bit about what a heat engine is. Okay, so now if I can take all of these arrows and simply reverse their direction. That's an allowable thing. So rather than having a net work output, I could input a certain amount of work. And as a consequence, the flow will go around in the other direction, you know, and as also the heat will be rejected at other, so the heat will be rejected on the hot side and absorbed on the cold side. And then when that occurs, I have what's called a heat pump or refrigerator. Now, a heat pump and a refrigerator are actually the same device. It's just whether we're interested in the heat being rejected at the hot side or the heat being absorbed by the cold side. All right, so we compress the fluid in a compressor, run it through a heat exchanger where the heat is where heat is rejected at the high temperature. It comes through an expansion valve, and then heat is absorbed on the cold side, and the cycle continues. Now, notice some of the devices have changed, but their function hasn't changed much. Okay, it's typically just due to I could literally just run this one backwards, but now instead of having a simple device like an expansion valve, which is inexpensive and simple, I'll have a more complicated mechanical device like the inverse of a pump. Like, so maybe I'll simply put like a turbine on this side and a compressor on this side and run it backwards, and I could actually recover some of the work and help drive the process that way. So it'd be more efficient if I had this. The process would be more efficient if I had a more complicated mechanical device. However, cost usually dictates the choice of going with an expansion valve over a more complicated mechanical device. But other than that, this device is essentially the same as this one with all of the arrows flipped. Okay. And just like before, we have a measure of efficiency. Okay. However, we don't call it efficiency per se. We call it the coefficient of performance, COP. Okay. And if we give it a little subscript, R for refrigerator. So this is a measure of efficiency. So what we have is desired quantity over the cost. And in this case, in the case of a refrigerator, I'm interested in how much heat I can absorb from the cold side. And the cost is the amount of work it takes. Okay? And just like before, the input work can be written as the difference in heats, just based off of the first law of thermodynamics like we did for the heat pump. So the COP refrigerator, you can plug that in, and the COP for a refrigerator can be rewritten as so I could rewrite it in terms of this sort of complicated fraction here. Now, the reason we would want to do something like that will become clear later. But so I can write it simply as the straight up desired quantity divided by the cost, in this case work input. And because of the first law of thermodynamics applied to this system, I could rewrite that in terms of the ratio of the heat. Okay. Now, the reason we call it a COP instead of just calling it efficiency is that it's typically greater than 1. And we'll get into some examples and stuff, but it's typically greater than 1. So rather than causing confusion or we just change the name. So it's a measure of efficiency, but because its value is greater than 1, we don't call it efficiency. We call it COP, coefficient of performance. Okay. But in reality, it's essentially a measure of efficiency. Now, the COP for a heat pump, again, is a desired quantity divided by a cost. But in this case, a system that's called a heat pump is really just, the difference is I'm just interested in the other side. So I can use this same system, pulling in heat at the same temperature and rejecting it to the same temperature. And if I'm more interested in the hot side than I am the cold side, then we call it a heat pump. That's the only difference. And so the desired quantity in this case would be the heat rejected to the hot side, and the cost is still the net work in, or the in this case, since there's no output work, it's just the work input. And again, using the same, applying the first law, I can rewrite the COP, a measure of performance, the coefficient of performance for a heat pump, in terms of the ratio of heat. So they're related and they're very similar looking, but you can see that the heat ratio is inverted and the sign on the bottom is reversed. Okay, so literally the same. I just want to repeat it. The difference between a heat pump and a refrigerator is which side you're interested in. And the measure of efficiency reflects that. Now, the second law, the second law of thermodynamics is has many sort of definitions, okay? And so we have to narrow our focus a little bit and talk about what it is that we're going to be interested in. We are interested in heat pumps, or I'm sorry, in power plants and refrigerator heat pump systems, okay? And we're primarily going to be looking at what's called the Rankine cycle, and that'll become clear here in a little while. So the second law in that context is simply the statement. There's two versions of this statement, and they wind up being equivalent. But there's a Kelvin-Planck statement of the second law, which states that heat engines must reject some heat. It's not a quantitative. That's not a quantitative statement, but it is a statement. Okay, and the consequences of that are that the heat rejected on the cold side has got to be greater than 0, and therefore the thermal efficiency must be less than 1. Okay, so the Kelvin-Planck statement is that heat engines must reject some heat. And the second law, applied to refrigerators and heat pumps, are just essentially the equivalent statement, but it's just that refrigerators and heat pumps require work input, which means I have to provide some heat in order to get, or I'm sorry, I have to provide some work in order to get that heat to transfer heat from a hot to a cold interface. All right. So that's really it. And it turns out that the Clausius, I'm not going to go into it, but that the Clausius and Kelvin-Planck statements are equivalent. They can be shown to be equivalent. Okay. Now it's not difficult to show. You can look it up, but essentially, I could use a device that I could use a heat pump, or I'm sorry, a heat engine with a thermal efficiency of 1 to drive a refrigerator, and as a consequence, I will be just naively transferring heat from a cold to a hot object without work input. And so through simple logic like that, you can see that the two statements are in fact equivalent to one another. It's not terribly important, but the upshot here is that heat engines must reject heat, and refrigerators / heat pumps must have heat, or I'm sorry, work input.